Today I am going to discuss the Schrodinger equation, and let us begin with the necessity of the wave equation and what are the conditions on the wave equation in the quantum mechanics we will impose. Now we have already introduced the wave function concept, and you know this psi is the wave function of the system, which is just describing the dynamical state of the system, that is the system in motion. So the dynamical state is described by the wave function completely. And now we also know the superposition of plane waves of different wave numbers to give rise the wave packet. Okay, so this was discussed in my earlier classes, so I am not going into this. Now that we know the wave associated with the moving particle is the matter wave, so one need to use the matter wave equation, and we will now find the matter wave equation under the light of Schrodinger's prescription. So let us begin with the fact that the equation cannot be derived, that is the Schrodinger equation cannot be derived like all the basic physical laws, like the Broglie hypothesis or Heisenberg uncertainty principle, which we come across in past, which these laws have no straightforward proof, that is those cannot be deducted, but those can be used to get some facts or results which can be tallied with experiments with other physical facts. So like this manner we will proceed to find the wave equation of the plane wave corresponding to a particle, of a moving particle. So the wave equation now here in quantum mechanics, actually this wave is matter wave, and actually the matter wave signifies the probability wave. I will discuss it later. So let us now note some salient features of this wave equation. That is, the wave equation must satisfy these following restrictions, which will be again coming from those old quantum theory or quantum mechanical facts. That is, it must be consistent with the Broglie hypothesis or the Heisenberg uncertainty principle. So the first one is linear and homogeneous equation it should be, and superposition principle will also hold. That is, if you get two solutions of the wave equation, which I have not discussed now. So suppose there is a wave equation, matter wave equation, and you have two solutions, psi1, psi2, then a1 psi1 plus a2 psi2 will also be the solution. That is, the superposition principle is valid for this case, and because this equation should be in linear and homogeneous forms, so superposition principle is obvious outcome of it. Now the differential equation will involve the time in first order of the equation, and the next one is Planck-Einstein relation holds, that is E is equal to h cut omega, that is h nu formula holds for the particle, and the momentum is equal to h cut k, where k is equal to 2 pi by lambda, you know. So this is the Broglie hypothesis also holds. So these are and also the correspondence principle. So these are the criteria to make the wave equation, which was made actually by great Schrodinger in 1926, which can be discussed in the following manner. This is not the original prescription of the Schrodinger, I am telling you. If you want to know how Schrodinger forms this equation, you can consult some standard textbooks like Matthews Venkatesan. There is some description how Schrodinger came into the into his well celebrated wave equation. So I am just taking the easiest path to get the form of the Schrodinger equation, time dependent Schrodinger equation, by assuming that the particle is moving, that is its matter wave is progressing in plane wave manner. So the plane wave solution is assumed. Psi is equal to a e to the power I px minus et by h cut. You know kx minus omega t form, so put in place of k. Oh, obviously here the one dimension problem is chosen, that is the particle is moving along x direction, so so k is substituted by p by h cut, where from the Broglie hypothesis. Here you can see k is equal to p by h cut, and vector is not there because it is one dimension motion, and another is omega is equal to e by h cut. You can replace it. So those are replaced in the form of plane wave solution, and a is amplitude factor. So if you differentiate this equation by one time with respect to t, and this will give you this formula, equation number 2, and if you differentiate this one 2 times, then you will get this formula, equation number 4. Now see, the right hand side of the equation is E psi, and equation number 2 and equation number 4 has p square by 2m into psi. If for non-relativistic free particle, that is particle is not under any kind of force, so the energy will be totally kinetic energy, so p square by 2m is equal to E. So right hand side of the both equation 2 and 4 are equal, so the left hand side should be equated, and it will give you this form: I h cut del psi del t is equal to minus h cut square by 2m into del 2 psi del x2. This is the one dimensional time dependent Schrodinger equation, because the wave function consisted of both time and position, but for the free particle. Okay, this will be formulated again by a more general treatment, by considering the wave is not a plane wave, because you know, if we assign a plane wave with the matter wave, then the plane wave is obviously the monochromatic, so the wavelength is definite, so momentum is definite, but the position will be completely undetermined, because it is a consequence of Heisenberg uncertainty principle. So the position, to determine the position and momentum with some uncertainty, that is delta x into delta p is greater than equal to h cut by 2, those we should keep in our mind. So the plane progressive wave is not possible for a moving particle under force free condition. So we here assume the more general form of the wave solution, that is wave function, which is 1 by 2 pi h cut integration phi p, and this one is nothing but the equation of the wave packet. And the wave packet, you know, it is localized, it is a localized free particle, that is a wave packet corresponding to the localized free particle. What is meant by localized, I will show you. Here you can see this is a form of a wave packet, you can see, and here the wave packet is formed by the superposition of theoretically infinite number of plane progressive waves with different frequencies, and this will give rise this kind of periodic function psi, which is wave function. But here the psi is localized. The localized means it is maximum at some point, but there is a spread of the wave function, that is there is a width, there is a half width of the wave function which is not equal to 0, and that half width is delta x, which is consistent with the uncertainty principle. In my forthcoming classes I will discuss it very in detailed manner, how this form of the wave packet is justified and consistent with all physical laws like uncertainty principle. So to make this wave packet, we should have infinite number of plane waves. Those are superposed, and here you can see the equation is like this. This is the superposition. Actually summation is there. Instead of summation there is an integration, because we have assumed that the frequencies of the wave or the wave vectors of the waves are different from each other by a very small dp amount, that is very delta amount, small amount. So it is a continuous system. We can assume that the different waves have different frequencies but in continuous manner. So the instead of summation there is a integration, and I have discussed this form. This is actually Fourier transform of this phi p into the space coordinate, and I have discussed in my previous classes. You go to this for the continuous basis. You can see the continuous cases, continuous basis, the wave function can be written like this by Fourier transforming it. Now you should if you assume this form, equation number 7, and then again follow the same path, that is differentiate this one with respect to time one time, and differentiate this one, this psi with respect to x twice. So this will give you the same right hand side, because E is equal to p square by 2m for the free particle. So this one I h cut del psi del t is equal to minus h cut square by 2m into del 2 psi del x2. So the similar form of the time dependent Schrodinger equation in one dimension for the free particle will got. And from this kind of discussion we can see, you can see from here, yes, this one, you can see this is a kind of eigenvalue equation. No, this is a kind of eigenvalue equation, you can see, because if IH cut del t is an operator, so this operator has eigenfunction psi with eigenvalue E and eigenfunction psi. So that operator is called energy operator, IH cut del t. So in resembling to that equation or comparing to that equation with the eigenvalue equation, you can write the energy operator will be IH cut del t, and similarly P is equal to minus IH cut del x, which we know previously. And this one is yes, and in 3D, if the particle is moving in 3 dimension, then the wave equation should start from P dot R. Instead of px, p into x, you should write p dot r, that is pxx plus pyy plus pzz minus et by h cut will be there, and there the momentum operator will be IH cut del, that is the naval operator, that is del operator, and this will give you the Schrodinger equation in 3 dimension for the free particle like this. Left hand side is same, but the right hand side is in place of del 2 del x2 grad square, del square will be there, which is the Laplacian operator. And if now we assume that the particle is under force, some force which is actually conservative one, that is can be derivable from the potential VRT. In general, the potential can be a function of time, so it is assumed that VRT, potential is a function of VRT, so energy will be p square by 2m into V. So if you get the operator form of this equation, so E operator, P operator square by 2m plus V operator, and you know V operator is multiplying, so operator sign is not there. And if you operate this on psi, which is a function of r vector and t, so you will get E psi is equal to p square by 2m plus V psi, and in explicit form you can write E operator as IH cut del t of psi, and here minus h cut square by 2m into Laplacian plus V over psi. And now this one is again a new operator. The left hand side is energy operator operating on psi, but the right hand side, this operator is called the Hamiltonian operator, because it is coming out of the kinetic energy plus potential energy. So kinetic energy operator and potential energy operator together with make the Hamiltonian operator. It is defined as Hamiltonian operator, and you have already shown that this Hamiltonian operator is Hermitian one. So all the informations you have previously, but here comes the Hamiltonian operator, and its role will be very much important later on, you can see. And now the properties of the wave function, you know this, but I am again reading out of those properties which are assumed to have a proper wave function, that is to become an acceptable wave function, that is well behaved wave function. You should have these properties. The wave function should be single valued, it must be continuous in the entire region of space, and it must be finite everywhere, and also square integrable, that is psi must be 0 where the distance is tending to infinity plus or minus infinity. So these are the conditions. And now interpretation of the wave function, a lot more. The first interpretation we have already come across, because it is the probability density, and you know the probability density is defined as mod psi square from Max Born's interpretation, and here it is written in 3D, and P is the probability density, which is the function of R, vector, and T, so is equal to mod psi square, that is psi star into psi. It is the probability of finding the particle with per unit volume at a point. And now if you integrate this one over the whole space, you will get 1, so that the probability of finding the particle in all over the universe is 1. So this integration is called normalization condition, you know this. And if this is true, yes, it is always true physically, so it will again telling you some another feature, which is that the probability is conserved. How probability is conserved? This means that probability is equal to 1. Probability of finding the particle all over the universe is 1. How does it mean that probability is conserved? Yes, of course, you can think of that you're finding the probability of yourself. Suppose you are in Kolkata, so probability of finding in Shialda will be some value, some fraction over there, and now you move from Kolkata to Bombay. So what is the probability of finding you in the Kolkata? Answer is 0. But what is the probability of finding in Bombay is 1. So 1 probability transforms from Kolkata to Bombay. So the total probability always conserved, always 1. So this is the meaning of probability conservation, and mathematically one can see if del t over this two sides is taken, so the right hand side should be 0 because there is 1. So del t over left hand side will give you 0. So that is, this equation is time independent, that is the probability is time independent, that is probability is independent of time, and thus it is conserved. So equation 21 is very much useful. I will come into that point. Now let us now express those things, and the question I have written here, no, I will discuss it later. Now let us use the Schrodinger equation in 3D, equation 22, and take the complex conjugate of both sides. Psi will be psi star and I will be minus I. So this will be in this form 23, And if one multiply equation number 22 by psi star from the left hand side, and equation 23 by psi from the left hand side, so and then subtracting two equations, one will get what, this one in the left side and this one in the right side. Now what is this? Let us now start from there. Now start from here. Psi star dr, here dr is the volume element, that is dx dy dz, and this is the volume integral over v. V is finite volume, so del t over this will be, the del t will be will go inside the integration. So psi star del psi del t plus psi del psi star del t will be there in the integrand. And now what is this? You have found it, psi star del psi del t. Here it is. No, actually whole thing is found. Psi star del psi del t, yes, equation number 24, the left hand side is the integrand of this equation. So I h cut will be brought in the right hand side. So this value should be put inside this integral, and this will be this, and you can easily prove that this one psi star del 2 psi minus psi del 2 psi star will be is equal to divergence of psi star grad psi minus psi grad psi star. It is done in your vector analysis classes, so just one line matter, you can check it. Now let us define this vector with the constant minus I h cut by 2m into this one as that is h cut by 2im into psi star grad psi minus psi grad psi star as j vector. So j vector will be this with this constant with the negative sign. So the above equation, that is equation number 25, will be del t over, here it is the probability density, that is PRT. So del t over P plus gradient divergence of j is equal to 0, because you can cancel these from both sides the integral, because V is an arbitrary volume. So the integrand should be equal from the both sides, and it will give you del p del t plus divergence of j is equal to 0. This equation is very much familiar to you. This is looks like the equation of continuity. In case of matter flowing through a medium, the density and the current density of the matter from the material or mass conservation law, you can write this equation of continuity. Where there is an equation of continuity, there should be a conservation of some physical quantity. In case of mass flow, there is a mass conservation. In case of current flow for steady current, same equations have arrived there, but with P as charge density, volume charge density, and J is a volume current density. So here, as the wave flows, propagates, that is the matter wave propagates, that is the particle is moving, what does it mean? What does the conservation law here? Actually, this is the conservation of probability, which I have talked earlier with the example of Kolkata to Bombay. This is the conservation of probability, that is where the probability flows out of some surface, that is the divergence of J, there will be decrease of some probability density, that is minus del p del t, because divergence of J is equal to minus del p del t. So this is the conservation of probability actually, and thus it is called the equation of continuity corresponding to the probability of the probability flow. So we can we can go backward and see where does this equation comes from. It is coming from the Schrodinger equation. So, and Max Born interpretation. So Schrodinger equation actually signifies the flow of the matter wave, that is actually the flow of the probability, that is, it is sometimes it is called the probability wave. Okay, and you can see here some features what I have talked to you earlier, that is from Max Born interpretation. This one is 1, so del t over this probability should be 0, and you can prove this from the equation of continuity as well. How? Let us integrate this equation over the volume V, and what suppose this equation 27. So let us take the equation number 27, del t over p dr, that is the probability of finding the particle within the V. So time rate of that probability is equal to minus divergence of j into volume integral. So by divergence of j can be written as surface integral, closed surface integral by Gauss's divergence theorem, that is j dot ds. It is written over here, you can see equation number 28. So j dot ds, and you if now v is expanded to infinity, that is I am willing to find the rate of change of probability for all over the space, then v will be expanded to infinity. So that surface, that closed surface S, will be at infinity. So at infinity, j, what is within the j? J is consisted of wave function, and you know at infinity the wave functions are 0. It is a well-bearness of the wave function I have just talked in this lecture. So wave functions vanishes at infinity, so j also vanishes at infinity. So this surface integral over the j dot ds will be 0, because the integrand itself is 0 at every point on that surface, which is staying at the infinity. So the right hand side is 0, so we have come into the same conclusion from the probability interpretation, that is del t over the probability of finding the particle on all over the space is 0. That is, the probability of finding the particle in all over the space is constant and is equal to 1 if the wave function is normalized. Now it is there is some interesting topic you can assign by resembling the steady flow, that is j is equal to is a function of velocity. You can find you can see in case of the steady flow, that is the probability current density is proportional to the velocity of the particles, and here you can see also the velocity of the particle is associated with the probability current density j. So the name is perfect probability current density. And one thing, very interesting thing, that if probability current density is not equal to 0, in general it is not equal to 0, so psi should be real. If psi is not real, psi should be complex. If psi is not complex, what happens? Psi is not complex means psi star is psi and this psi star is also psi, so two terms will be cancelled, so j will be 0. So wave function will be complex, and because of that fact I have started also the fact comes from the assumption that is psi, we have taken that in complex form. So the wave function and the Schrodinger equation regarding the matter wave, that is the probability wave, is discussed, and this will be kept in our mind throughout the quantum mechanics. As long as you are reading quantum mechanics, those inner tidbits will be constantly in your mind. So it is very necessary to understand the unitarity of the time evolution problem in the quantum mechanics. What is that? You have the wave function or the state vector which is describing the dynamical system, and you know the wave function at some time, and you want to know what will be that wave function at the latter time. That is called the time evolution. Similarly, operators which are depending on time, the question is same. You have the operator which is at some time, and latter time what will be that operator. This is again the discussion will be this discussion will be depend on the time evolution problem in the quantum mechanics, and you note that the time evolution is unitary. So to understand this, I am going to discuss it using the Schrodinger picture. Now you should know that some operators or the wave functions, and depending upon the wave function and the operators, there are some descriptions in quantum mechanics which are called the picture of quantum mechanics. There are three kind of pictures: Schrodinger picture, Heisenberg picture, and the interaction picture. The Schrodinger picture, where the operators do not explicit function of time, but the wave function is explicit function of time. In Heisenberg picture, the wave function, the operators are explicit function of time, but the wave functions are not. So those pictures I am not discussing here. I just focus on the Schrodinger, and I have forgot to mention in the interaction picture, both the operator and the wave functions are explicit functions of time. So here the topic of discussion in your syllabus is the Schrodinger picture, where the wave function or the state vector, it is written in the preceding section. I will use the direct notation. So psi is a function of time explicitly, but the operators are not, and the time evolution of the state vector is controlled by the Schrodinger equation. I have just described to you that the wave function, the Schrodinger equation, is nothing but the wave equation. That means wave is now at here. What will be the phase of the wave at there, that is at latter time? This is the wave equation. So Schrodinger picture being a wave equation, it should have some time evolution property, but not on the operators, on the state vector, that is wave function. Now consider this. This is written in operator form. I h cat del t, that is energy operator, on psi is equal to Hamiltonian operator over psi get. Now let us suppose the evolution operator is u, which is a function of t and t0. T0 is the initial time, where the system you are going to watch the system, or you are going to measure the system initially at t0 and at latter time t. So t must be greater than t0, and you have, suppose you know this wave function psi t0, that is at initial time the wave function is known to us, and the wave function at latter time psi will be is equal to u operator operating on psi. So what is u? I don't know. At this point of time I don't know about this. We have to find this. So the expectation value, or the it is called the length or the norm of the wave function, that is psi, you know this. Actually this is the probability, inner product you can say, that is the probability of finding the system at time t. and the probability where the probability is counted in the spatial coordinates, that is you are just calculating the probabilities at different positions in space. So this is this integral is not over the time, this is integral over the space. So psi, that is the norm of psi, is equal to what you can write from here. You can find the bra of psi and put it down here. Put the form of the psi here, and you know the formula for bra. U operating on psi within the bra can be written as bra psi u dagger, and the right hand side you can take out this u operator out of the kit without any daggering. So u operating on kit psi, both are at t0. Now this should be is equal to psi at t0. So psi at t, that is length of psi at instant t, should be equal to the length of psi at t0, because the integration within the inner product, this is actually integration psi star psi d tau over the all over the space. So that should be is equal to, exactly, if this is normalized, it should be 1, and this should be 1 also, because in time, remember my example, that is you are in Kolkata, then your probability of finding you in the Kolkata is 1, but in Bombay it is 0. But you move to Bombay, so the probability of finding yourself in Bombay is 1, but in Kolkata is 0. So but the probability of finding, if one calculate the probability of finding you in the whole universe, it should be 1 always. So the probability, that is the inner product of psi, that is the length of psi at t0, should be equal to the length of psi at t. So in doing so, this one should be identity operator, otherwise this should not be possible. So u dagger u should be identity operator. Similarly, you can proceed in reverse way and you can write that u dagger is identity. That means u should be, u is such an operator, it is called propagator, or it is called evolution operator, because this operator is function of both time, latter time, and the initial time. So this operator is bringing this wave function into the latter time, so that that is why it is called the evolution operator or the propagator. That is the courier service. You posted a letter in front of the courier, and later time another person will get that letter. So the intermediate transition happened by the courier person. So courier person is the operator, or courier person will be the propagator, which propagates your letter. So that is why the name comes from in our practical experiences, that you will be the evolution operator or the propagator operator. And this is actually the unitary also because of this condition. Okay, so this is the unitary operator. This should have the unitary nature because of the conservation of probability. It should be unitary, and you can write those formulas. That is nothing but these are the properties of unitary operator I have discussed in my previous class. Now if you substitute this equation, if you substitute this psi u on psi t0, psi t is equal to u operating on psi t0 on this Schrodinger equation, then this will give you here this will give you this equation, because psi will be cancelled from both sides, psi t0, because hu0 here you can see, in place of psi t you can replace u operator and psi t0, but psi t0 is not a function of t, So it will be del t will not be acting on this, but del t will be acting on u operator, and similarly here u operator will be there and multiplied by psi ket t0, psi t0 ket. So psi t0 ket will be cancelled from each other, from the both sides, and you can write this form I h cut del u del t is equal to h operating on u. Okay, now you can integrate this. Okay, you can integrate this over time from t0 to t, and you can, yes, here you can see the form, that is psi u at t0 comma t0 is identity, because utt is always ut t0 is identity. No, utt as is identity, because if you replace t0 by t in this equation, you can write, or you can replace t0 in place of t, you can write u dagger t0 t0 u dagger u t0 t0 is equal to identity. Now u dagger is equal to u, so it is u operator square is equal to identity, so u should be an identity, that is u t0 comma t0 is identity, or utt is equal to identity, you can write in either way. So u t0 t0 is identity operator. So this will be the lower limit of this equation, because the lower limit is t is equal to t0 and the upper limit of the integration will be t is equal to t. So in the lower limit you can bring this u the denominator and find the solution like this. This will be log of u operator. Suppose that operators are just like variables, so you can operate in that way, so that this will give you the result. I h cut will be in the right hand side, so minus I by h cut will be in the right hand side, h operator will be right, and del t will be in the right hand side also. So the integration, after this integration you can get log of u is equal to minus I by h cut into h operator into t minus t0 actually. So put the log in the right hand side, so eliminating log from the left hand side, you can write u operator function of t comma t0 is equal to this one, because your u t0 is I, so log over I is 0, so this will be result, that is u operator is equal to e to the power minus I by h cut into t minus t0 into h operator. Okay, so this is the form of the unitary operator or the propagator of the wave function. Okay, so you can put this into the wave function. Now you can see how the wave function propagates. You know t0, so what will be the wave function at latter time? T is equal to say 5th second, so put this 5th second at this, and if t0 is equal to 0, that is your initial time is t is equal to 0, then t0 is 0. So you can get the time dependent equation from a time independent equation, that is psi at 0, from there also. And you know the basis set expansion technique, and also you can use this, that is at t is equal to t0, that is initial time, psi function of q means anything, any coordinate, it may be x, y, z or r, theta, phi, any one of them. So a q comma t0 is equal to sum over cm phi m. It is written in basis set expansion, where phi m's are the orthogonal wave functions, orthonormal wave functions, and those are basis wave function. And now you can dissolve the propagate into Maclaurin series like this, just expanding the e to the power series. and propagate and operate this one on this equation, on this wave function psi at t0. This will give you psi at t. So here you can see it is the propagator, sorry, this one is the propagator, and the latter one is psi at t0. So this will give you the result at psi at t. So operate this, that is h to the power n, if it is operating on psi m, this will give you, yes, here it is written h operating on phi m give you em0 phi m. 0 stands for it is time independent, that is at initial time it is the result of energy is em0. So each of term will contribute to em0 into t minus t0 whole to the power n. So it is written over like this using the eigenvalue equation. You can get this, and again it is an exponential function. This sum is exponential function, so sum over cm phi m e to the power minus I by h cut em into t minus t0. It is the complete set solution of the Schrodinger equation. This is the actual Schrodinger equation solution. So one has to find two things. One, the form of the energy or the energies in the physical or real problems. You have to find the energy eigenvalues and the wave function, that is phi m, that is the basis. If you know the basis, you know the energies, then you can write the whole solution, that is the complete solution of the Schrodinger equation, which is in equation number 13. So now let us take the next topic, which is the time evolution of the expectation value. How the expectation value of a dynamical variable evolves with time. For this is the formula of expectation value as psi is normalized. You can write this psi a psi. Now the Schrodinger equation is ih cut del del t over psi is equal to h operator psi, or you can write in the right hand side, you can take ih cut in the right hand side, so minus I by h cut into h operator over psi. So the bra, you can take the Hermitian conjugate or Hermitian adjoint on the both side. It will give you del del t over psi, but it is in bra, and here in the right hand side I will be replaced by minus I, so I by h cut, and the order will be reversed. So bra psi into h dagger will be there, but h dagger is h because h Hermitian, h is Hermitian. So these two results will be used, this one and this one. These two results will be used. How the expectation value, we want to evaluate the time evolution, that is how the expectation value of any dynamical variable changes with time. So ddt over a will be done. So ddt over a will be this del del t over bra, because a is what? A is made up of three terms, psi, a and this one. For the time being, let us suppose that a is a function of time also, that is it is not in Schrodinger picture. Okay, so three terms will be there if you differentiate with respect to time. First, the differentiation of the bra with respect to time, next the differentiation of the kth with respect to time, and then the differentiation of the operator with respect to time. So three terms will be there, and the del del t of the bra psi is given here. Del del t over the kth psi is given here. So put them all and do some minimum algebra. You will get from the first two term as I by h cut psi bra psi, the commutator bracket over h comma a psi t plus the rest of the term, and you can take this one within a single operator, that is I by h cut into commutator bracket of h comma a, or a comma h, taking the negative negative sign and I at the denominator, and the last term is del a del t. So this is the new operator. This is the new operator form. So one can equate that, or one can not equate. This is the expectation value, or I should bracket this one. Yes, this is what psi at bra, psi at ket, and within this this is another new operator. So this is the expectation value of this new operator. What is that? I by h cut a h plus del a del t. This is the expectation value of this whole new operator. So it is written like this. So I by h cut into expectation value of a comma h plus expectation value over del a del t. This is the equation of motion of the expectation value or the equation of motion of any dynamical variable. Okay, this is actually the bridging path, or this is actually the bridge of the quantum mechanical result to the Newtonian mechanical result. I will show it later. Let us now look a very interesting fact, that if the operator is not an explicit function of time as it is in Schrodinger picture, so del a del t term will be 0. So dA dt will be 1 by h cut I h cut a comma h. And now if the dynamical variable commutes with Hamiltonian, so this term again will be 0, a comma h will be 0. So dA dt will be 0, so a will be constant. It is written over here. You can see, if commutes with h and not a explicit function of time, then the total time derivative of a expectation is equal to 0. So a expectation is constant. That means that variable is constant of motion. Okay, you know that Hamiltonian momentum or angular momentum commutes with each other. Yes, and linear momentum sometimes not will commute with Hamiltonian, but generally it will commute. So these are the commutating observables h, p and l. So you can write dh dt because h is always commuting with h, so it is also there. P also sometimes commute with h, so p is conserved. And l, if l always commute, so h comma l is also 0. So these are the constant of motion. Okay, so Hamiltonian is a constant of motion. Momentum, sometimes if it commute with Hamiltonian, then it will be a constant of motion. Recall your classical mechanics classes. Say for example, say your central force field. What happens there? The angular momentum is constant, so its time derivative is 0. Okay, here angular momentum in quantum mechanical description, you should first check whether the variable commutes with Hamiltonian or not. If it commutes, and if that operator or that observable do not involve time explicitly, then that operator or that dynamical variable will be constant of motion. That is, its expectation value will be constant. Okay, this is the bridging of the conservation theory between the quantum mechanics and the classical mechanics. And the linear superposition principle, you know this, I will not go into this detail. And by linear superposition principle, you can describe the double slit experiment and I will talk it later in, but yes, I am just briefing this thing. In double slit experiment, two slits are there, A and B, and this is a source of electron, and if electron passes through these slits, it will be collected into the screen. Here the C is the collector, that is the recorder. It will record the number of electrons that come to the screen, and this is the midpoint of the screen, and X is the position of the distance of the collector or the point of investigation from the midpoint of the screen. So if the experiments done in 4 cases, where in first case the slit A is off, that is A is shut down, A is blocked, and then B is blocked, then both A and B are open. Okay, 3 steps. The first, if A1 blocks A, then he will get this result, that is the number. This here intensity signifies the number of electrons. So number of electrons will be greater at some point because of the diverging nature of the beam, and if the slit B is stopped or blocked, then no, first case the you blocked the B slit. That is why the maximum density of the electrons forms at in front of the A. Here the maximum intensity forms like this. If you block B, so no electrons will come out of B, so you will get a higher density in front of A, and reverse phenomena will happen when you block A and open B. In this region the higher density of the electron will be found. So there, but when they both are present, so maximum intensity will be in this region, classically in this region, sorry. So this will be looking like this, but the experiment shows this like picture. So double slit interference pattern with diffraction effect is there. So how to discuss it? To discuss it, let us assume the superposition principle. I have discussed this result earlier but not discussed the experiment before. So go through these results, you will understand this thing, how the superposition principle leads to the only description of the quantum mechanical interference effects and the double slit effect also. Now the Ehrenfest theorem, which is the quantum mechanical counterpart of the classical mechanics law, how it is formed, I am showing you. If A is an dynamical variable and it is not explicit function of time, then you have this equation of motion. I have just discussed it. dA dt is equal to 1 by h cut A comma h expectation. Now let us suppose A operator is x, that is the position operator. Let us examine 2 operators, one by one. First the position operator and then the momentum operator in one dimension case. So dx dt is equal to 1 by I h cut x comma h, and if you put p, then p comma h will be there. Here h is what? P square by 2m plus vx. Now v is the multiplying operator. So x comma h means x comma p square by 2m plus v. So distributive law, using the distributive law, the commutation bracket x comma px square, we know that thing, it is I h cut px by m. So it is very simple. In my previous class I have discussed a lot about those commutation relations, so use those and you will get some interesting result, I h cut px by m. So put this result into the expectation, I h cut will be come out and cancel, or 1 by m will be come out. So 1 by m and expectation value of p So dx dt is equal to p expectation value divided by m, which is just like the classical result, that is momentum is equal to mass into velocity, just like that. But here you should remember that here the values are expectation value, but this looks like the classical mechanics result. And the most thrilling result is this dp dt, because it is Newtonian like result. dp dt is rate of change of momentum. What we will get in the right hand side, if it is classical mechanics, you will get the force. So px comma h will be very interesting to find out. Now px h consisted of p square operator, so first px comma px square is 0, and the next part is v. So px comma v is equal to nothing but minus I h cat del v del x. So this one, so the whole commutation relation is minus I h cat del v del x. So the expectation value of this divided by I h cat, it will be minus I h cat will cancel each other, and del v del x expectation value. Now del v del x, what is that? It is the differentiation of potential with respect to position, that is the conservative force. So rate of change of momentum is equal to force. Actually it should not be like likely stated like I have stated. It should be stated like, that is the rate of change of expectation value of momentum is equal to negative of the expectation value of dv dx or del v del x. And in classical mechanics, it is the rate of change of momentum is equal to force. No expectation terms are used there. So this is the Newtonian mechanics, Newton's law in terms of quantum mechanical point of view. So Ehrenfest theorems just take you to the bridge where the bridge is connecting two worlds, one classical world and another is quantum mechanical world. So at this note I will stop my lecture, and thanks for listening.